I'm Don, N4DJ, and this is a PowerPoint presentation I put together based on my 80-meter half-square experience. I want to make this clear that this 80-meter half-square is a DX antenna. This is not necessarily good for local nets. To work DX, you need a low radiation angle. More power focused at the low angle equals better DX results. I designed for about 15-degree radiation angle. I compare antennas at about the 15-degree elevation angle. Now this is a typical chart of wave angle versus distance for a single hop. And typically the lower the angle, the better distance you get. 15 degrees is right around the center of the chart. Now with a horizontal antenna on 80 meters, you've got to get them up really high for low angle radiation. Horizontal antenna, a half wave high, has a peak radiation at about 30 degrees. 120 feet on 80 meters is about a half wave. For a 15-degree peak, you need to be at least 245 feet high, and that's pretty hard for most of us to do. Looking at the gain of an 80-meter dipole versus height. At 60 feet, your gain is negative 0.8 dBi. At 120 feet, 4.7 dBi, and at 240 feet, you get your 7.75 dBi gain. Now, I like to use the dBi term. dBi is gain in reference to an isotropic radiator. It's not exactly a real antenna. 0 dBi is the equivalent of all your power radiated equally in all directions. Now, a dipole doesn't do this. A dipole has some gain off the sides. That's why you see a gain of a dipole at 5, 6, or 7 dBi. A vertical usually radiates equally in all compass directions, but not straight up. Now, a lot of people ask why use dBi as a reference. Well, it's easy to calculate what signal you would have if all your power was radiated equally in all directions. It's easy mathematically. Now let's look at some plots of some antennas. This is an 80-meter dipole at 60 feet. And you can see where all the power is going. Pretty much straight up. And here's an 80-meter dipole at 60 feet. Gain is 0.86 dBi. So it's not a whole lot of gain at the 15-degree elevation angle. Moving the dipole up to 120 feet, you get about 4.7 dBi gain. And you're starting to form a pretty good elevation lobe. 4.7 dBi at 15 degrees with an antenna or an 80-meter antenna 120 feet high. So that's not bad. That's a pretty darn good antenna. Now, how high should I go? Well, to make that horizontal antenna really work on 80, you need to be 240 feet for maximum gain at 15 degrees. Now, that's like having a 20-meter antenna at about 60 feet. Now, a dipole at 240 feet has about 3 dB more gain than one at only 120 feet. Cause what if I can't get that high? Well, if you can't get really high on 80, the answer is to use some sort of a vertical antenna. Now, with a vertical antenna, you have some advantages. Verticals are not dependent on height above ground for a low takeoff angle, like a horizontal antenna. The quality of ground in front of the vertical is important. This can also be a disadvantage. Disadvantages of vertical are that you need a good ground system. That's mandatory. Now, excellent ground system is desirable. Quality of the ground in front of the vertical is important. Can also be a disadvantage. Low loss ground at vertical is very important. Note, the two grounds are not the same. Now the half square is not your conventional vertical. It has the low angle advantages of a vertical. It does not need an extensive radial system. It can be fed directly with coax. It does not have to be a full quarter wave high. The 15-degree gain of a half square is 6.2 dBi. The 15-degree gain of my version is 5.8 dBi. And remember, the 120-foot dipole has a gain of 4.7 dBi. Now, there's several ways to think of a half square. The half square is half of a square loop. The vertical sides are quarter wave verticals. The horizontal wire is 1/2 wavelength long. The two vertical sides make up a phased vertical array. This is sort of like an off-center fed dipole with the ends bent down. Now this is a depiction from EasyNet modeling. This shows the top half of a square loop. I'm using like 4 segments here. The current distribution, note the low impedance points at the 2 top corners. On the half square, the maximum current is at the top of the vertical. This is the current distribution on your conventional bottom fed vertical. It has minimum current at the top and maximum current at the ground. The half square is exactly opposite of this. Another major factor for the half square is it doesn't have to be 65 feet high to work extremely well. We find the bottom ends of the half square can actually be bent in to compensate for the lack of being able to get the supports up a full quarter wave. This is showing the current distribution on the bent half square antenna. At the ends of the antenna, there's a very low current, so you can sacrifice the ends by bending them in and not lose much. Now we're looking at the 15-degree elevation gain of 80-meter antennas. A full-size half square has a gain of about 6.2 dBi. The bent half square is 5.86. The dipole at 60 feet is negative. The dipole at 120 feet is 4.7 dBi. And a dipole at 240 feet, that's what it takes to beat the half square, 7.7 dBi gain. Okay, so how low can you go? Well, suppose you can only go 35 feet high. Can you bend it more to compensate for the lack of height on an 80-meter half square? Well, let's see. A bent half square only 35 feet high has a gain of about 5.19 dBi. So that's actually worth doing because it'll still beat a dipole at 120 feet. Okay, what kind of ground do you need? Well, most of my models use very good ground. That's because that's what I had in Fox Hill. The next chart shows my half square over average ground. EasyNet predicts about 3.6 dB gain. Now this chart factors in the bent half square above average ground at 2.24 dBi. Unfortunately, I'm still listing the dipole at 60, 95, and 120 feet over very good ground. So these numbers are a little bit inflated. The half square at 2.24 dBi is above average ground. You can expect the dipole at 130 feet to be quite 5.7 dB. It'll be somewhat less because if it's over average ground as opposed to very good ground. The bent half square over average ground compares with a dipole 95 feet high. The bent half square over very good ground compares with a dipole 130 feet high. This shows a full-size half square pattern, elevation pattern versus a bent half square. There's not a whole lot of difference in those two patterns, mainly because there's very low current at the ends of the antenna where we bent it back. This shows my half square versus a dipole at 120 feet. I have a little bit better lower angle gain than the dipole at 120 feet. However, the dipole 120 feet is a little bit better at some of the higher angles. This shows, this is a no-brainer. The N4DJ half square versus a dipole at 60 feet. The half square wins at almost any elevation angle. Useful for DX. This is, again, my EasyNac antenna view, showing the antenna fed at a top corner with 50 ohm coax. And this is the EasyNac wire table. Pretty simple to model the antenna in EasyNac. And this shows the size of the half square. I took it down, rolled it up, hung it on the garage wall, and it's ready to go back up again. Not a whole lot to it. Pretty inexpensive antenna to build. Full-size verticals. Ultimate would be over seawater. Peak gain in that case would be about 5 dBi. Yeah, this shows the ultimate vertical over seawater with a very low angle, very low angle gain. And this shows my half square versus the ultimate vertical. The ultimate vertical wins at very low angles, if you can believe the EasyNac prediction on these ultimate verticals. Above 9 degrees, the bent half square wins. At 9 degrees and below, the vertical wins. Again, this is a theoretical modeling. So maybe not. At very low angles, vertical antennas, the ground reflection gets shifted in phase. So normally there's a 180-degree phase shift when the horizontally polarized waves are reflected from the ground. Normally there is a minimal phase shift when vertically polarized waves are reflected from ground, except at very low angles, like 9 degrees or less. Now, I'm a little bit skeptical about predictions for verticals below about 15 degrees. So I sort of recommend you take them with a grain of salt unless you're in free space. It's okay to compare two verticals at low angles because they are probably both equally affected. Now, here's a plot of the bent half square compared to a vertical over very good ground. The half square is significantly better than a vertical over very good ground. And as a matter of fact, the half square is about 3 dB better at the 17-degree elevation angle. It's better at all elevation angles. Now, what about azimuth angles? What is the pattern like on the half square? Well, the half square is directional. It is bidirectional, broadside, whereas the vertical is not directional at all. Now, this shows the pattern. You can't get something for nothing. So if you want gain off the broadside, you're going to have to sacrifice it off the ends of the half square. Now, this is the pattern of my half square, the way I had it oriented. It was good from about 30 degrees to 90 degrees. I had it pretty much erected for Europeans. And this shows the pattern when I had it up and pointed toward the Pacific. No trouble working Guam and JAs with it in that direction. However, I couldn't work Europeans worth a hoot. So how to best cover the world? Antennas ought to be broadside to the desired direction if you only have one. installing 2 half squares is definitely a good option. It really takes 2 to cover all directions. Now this shows the pattern of the half square versus the 60-foot high dipole. The half square is actually better in almost all directions. In fact, it's better in 260 of 360 degrees. Now here's the SWR curve. It's a fairly narrow bandwidth. You tune it for CW or you tune it for phone. I actually had extensions that I added to mine to get it from phone to CW. This is the SWR curve is measured with a device that K5VIP brought over to test with. The SWR bandwidth. The 2-to-1 bandwidth is about 80 kilohertz. Operating with a high SWR does not seem to affect the performance with a corner-fed half square antenna. It would if it was a bottom-fed antenna at either end. Electrical symmetry is critical. You get symmetry when you feed it from a top corner. Physical symmetry is also important. Here are some pictures of the bottom of my half square. It comes down and I've got it tied off and then bent in. That's not a real clear picture. And this shows the antenna coming down to an insulator and then bent to the left. I've got it maybe 10 feet or so parallel to the ground. The bent half square, does it really perform as well as these EZNet predictions would have you think? Well, my answer is yes, it does. That's a short answer. Yes, it does perform very, very well. Now you might ask, well, why do I think that way? Well, the actual results. The antenna was installed in December 2003. I worked 146 countries on 80 meters. On the air tests pretty much confirmed all of the EZNet predictions. I consistently beat 80-foot high inverted V's and dipoles under 100 feet. I proved it in CQ Worldwide and ARRL DX tests. I worked 82 countries on 80 meters in 6 hours in the 2010 CQ Worldwide DX contest. I worked 78 countries on 80 meters in the 2011 ARRL DX contest. I had more QSOs on 80 than any other single op station in Virginia, and I only spent 5 hours on 80 meters in the 2011 ARRL CW DX contest. That shows the antenna worked really, really well. And this is a clip out of the ARRL database for the 2011 contest, showing the countries worked on 80 meters and the QSOs. Now there are some variations of this antenna that you might say are on the drawing board. My friend W3TB suggested a variation using a switch, which would require only 3 supports for getting 4 directions. It'd be equivalent to 2 half squares at 90 degrees. EZNet predicts it will work. I haven't had time to build and try one yet. Trying 160 and 80 meters on the same antenna. Well, I don't think so. I don't think that's going to work so well. You could add a parasitic element. EZNet modeling indicates the 15-degree gain can be increased from 5.9 to 8.9 by adding a parasitic reflector. That's a definite possibility. This shows the half square with a reflector. you'll gain in one direction, but you'll lose bidirectivity. May or may not be worth trying. This is the 2 elements versus a 240-foot high dipole. Theoretically, a 2-element half square could beat a 240-foot high 80-meter dipole. Compared to a really good antenna, the 2-element half square of a very good ground is about 3 dB down from a 2-element quad at 100 feet. So that's not too shabby. This is a picture of the 2-element quad versus the 2-element half square. The quad being 100 feet and the half square being significantly lower. Now let's touch a minute on a 4-square array. Modeling of a 4-square array on 40 meters indicates the gain at 15 degrees is probably 7.2 dBi over very good ground, 4.5 over average ground. And I wouldn't think the gain would be much different on 80 meters. The predictions are the full-size 4-square is better than the half square, but not by very much. Over very good ground, the 4-square may be 1 dB better than a full-size half square, and the 4-square may be 1.4 dB better than the N4DJ bent half square. More detailed information, if you want, can be had from the ARRI antenna book, the ON4UN low band DXing. I recommend the 5th edition only. Or my email is n4dj@arrl.net.